3Blue1Brown, the hairy ball theorem, presented by Sanderson, running about 30 minutes. This is pure math at its most delightful. Grant takes one of the most ridiculously named theorems in mathematics and turns it into a beautiful exploration of topology, vector fields, and a genuinely elegant proof involving imaginary fountains and sphere orientation. If you have ever wondered why mathematicians care about combing fuzzy spheres, this video will make you care too. Section 1. The setup and the silly name. Grant opens with a personal touch, noting that the swirl of tiny hairs on the back of his 7-month-old baby's head reminds him of the hairy ball theorem every single time. The informal statement is simple and memorable. If you have a ball completely covered in hair and you try to comb all the hair flat, there is mathematically no way to do it without at least one point where the hair sticks up. You can try combing counterclockwise around an axis, but then the top and bottom will have little swirls where the centermost hair has nowhere to go. It is forced to stick straight up. What makes this fun to think about is that no matter how clever you get, it is a mathematical guarantee that at least one tuft will remain. Even getting it down to just a single problem point instead of two is surprisingly tricky. Grant encourages viewers to pause and think about how that might work, promising to show one method later. But first, he addresses the obvious question. Why would any mathematician care about combing fluffy spheres? The answer, of course, is that they do not. The name is tongue-in-cheek. The real mathematics underneath has applications that pop up in surprisingly practical places. Section 2. The video game problem. Grant presents a wonderfully intuitive motivation through a game development scenario. Imagine you are programming a game with a 3D airplane model flying along some trajectory. Your job is to orient the plane correctly as it moves. You know the nose should point along the tangent vector of the path, but that still leaves one degree of freedom. How is the plane rotated about its nose to tail axis? Where does the wing point? As a resourceful and lazy programmer, you might think you can just pick some perpendicular wing direction for each possible heading direction and have it vary continuously. After all, for any given heading, you have infinitely many choices, an entire circle of options. How hard could it be? This is where the hairy ball theorem strikes. Choosing a perpendicular direction at every point is equivalent to defining a tangent vector at every point on a sphere. And the theorem says you cannot do this continuously without at least one zero vector somewhere. In practical terms, any function you write to orient the plane based only on its heading direction will have at least one direction where the plane glitches. You simply cannot avoid it using velocity alone. You need more information from the trajectory. Section 3. Wind and radio waves. Grant offers two more real-world applications that are genuinely surprising. First, think about wind velocity at every point on the Earth at some constant altitude. If wind varies continuously, then the hairy ball theorem guarantees there is always at least one place where the wind speed parallel to the ground is exactly zero. Not that the air is still necessarily. It could be going straight up or straight down, but the horizontal component must vanish somewhere. That is a counterintuitive result that holds regardless of how wild the weather pattern gets. The second example is even more elegant. Suppose you want to build a radio antenna that broadcasts an identical signal in every direction of 3D space. Same phase, same amplitude at every point equidistant from the source. Electromagnetic waves oscillate perpendicular to the direction they travel. So at a given distance from the source, the oscillation direction defines a tangent vector field on a sphere. The hairy ball theorem says at least one point of that field must be zero. Therefore, the only way to have a perfectly identical signal in every direction is for the signal itself to be zero everywhere, which defeats the purpose entirely. This is why real antennas always have radiation patterns with nulls and lobes. Section 4. The puzzle of one null point. Before diving into the proof, Grant poses a delightful puzzle. Most vector fields you can dream up on a sphere seem to need at least two null points, like the north and south poles of a magnet. One swirl going one way, another going the other way. A source at one point, a sink at another. It is tempting to suggest there must be some universal law requiring at least two opposite null points, but with a little cleverness, you can actually get just one. The trick uses stereographic projection, one of mathematics' favorite mappings. You imagine a light shining from the North Pole. Every ray passing through a point on the sphere also hits exactly one point on the XY plane, and vice versa. Take a constant vector field on the plane, always pointing one unit to the right. Project it back onto the sphere. This gives you a vector field that is non-zero everywhere except the North Pole. Grant shows this beautifully as a fluid flow on the plane being projected onto the sphere, where the flow lines form perfect circles, all mutually tangent at the North Pole with zero velocity there. It is a lovely construction that proves one null point is achievable. But can you do zero? That is where the real theorem kicks in. Section 5. The proof by contradiction. This is the heart of the video and where Grant gets genuinely excited. The argument comes from mathematician Senia Shadevisor, and it is, as Grant says, just beautiful. The structure is a proof by contradiction. Assume a non-zero continuous vector field on the sphere exists. Then show something impossible must follow. Here is how it works. For each point on the sphere, look at the vector attached to it. Slice the sphere with a plane defined by that vector and the radial line to the origin. This plane intersects the sphere at a great circle. Now let the point walk along that great circle in the direction of its vector until it reaches exactly halfway around. The result is that every point P ends up at negative P, the point directly opposite where it started. Because the motion is defined by the vector at each starting point, and the field is continuous, nearby points have nearby trajectories. This creates a continuous deformation that turns the sphere inside out. But wait, there is a deep technical question lurking here. What does inside out even mean? Grant explains orientation using coordinate systems on the sphere, latitude and longitude labels that travel with the surface during any deformation. Using the right-hand rule with the index finger along increasing longitude and the middle finger along increasing latitude, your thumb points outward. This defines the outside with respect to the coordinate system. When you map every point P to negative P, these normal vectors end up pointing inward instead of outward. The sphere has been turned inside out. Section 6. The fountain argument. Now comes the beautiful contradiction. Grant asks you to imagine a fountain at the origin, spewing water uniformly in all directions at 1 liter per second. The flux, the net amount of water flowing through any surface surrounding the origin, must always equal 1 liter per second. This is true even if you warp and deform the sphere, because the water is incompressible and has constant density. Every bit of water produced at the origin must be cancelled by one exiting the surface. Crucially, flux is counted with a sign. Water going from inside to outside is positive. Water going outside to inside is negative. If the surface folds over itself, some regions count positive and some negative, but the net flux stays at 1 liter per second. Here is the key insight. The only way the net flux through a surface can change is if part of that surface crosses through the origin. If you push the sphere to one side so the origin is no longer inside it, the net flux drops to zero. But our hypothetical deformation from the non-zero vector field does two things simultaneously. First, it turns the sphere inside out, so the net flux would need to end at negative 1 liter per second, since all the normal vectors are now pointing inward. Second, no point ever passes through the origin because each individual point follows a half circle centered at the origin. These two requirements are flatly incompatible. The flux starts at positive 1 and can never change because nothing crosses the origin, yet it would need to end at negative 1 because the sphere is inside out. Contradiction. Therefore, the non-zero continuous vector field we assumed cannot exist. You truly cannot comb a hairy ball. Section 7. Higher dimensions. And the pattern. Grant closes with a fascinating observation about other dimensions. You can comb a fluffy circle with no problem. And in general, spheres in even dimensions can be combed, but spheres in odd dimensions cannot. The proof they just explored offers a direct clue for why. In odd dimensions, the function mapping a point to its negative reverses orientation, which is what drives the contradiction. In even dimensions, this same function preserves orientation, so the argument does not apply. Grant challenges viewers to construct explicit examples of non-zero vector fields on even-dimensional spheres, like the hypersphere in 4 dimensions. Key takeaways. The hairy ball theorem says no continuous tangent vector field on a sphere can be non-zero everywhere. It has real consequences in game programming, meteorology, and antenna design. The proof via the fountain flux argument is one of the most elegant in topology. You can get down to a single null point using stereographic projection, but you can never eliminate them all. The pattern across dimensions is that odd-dimensional spheres cannot be combed while even-dimensional ones can. And if nothing else, You will never look at a baby's head swirl the same way again.